Okay, fantastic. So I know it's been a long day and it's a bit late, and I'll try and make this kind of a bit fun. The topic is intentionally kind of mysterious. Doesn't mean anything, and that's what you get when you ask people to suggest the conference talk 6 months in advance. So basically, this allows me to talk about anything I want. And one thing that I would like to talk about is how cloud deployments are going to change testing, and how they're going to change risk profiles, and how they're going to change what we need to do to look at quality from kind of all different perspectives. One thing that's really, really interesting that I read, there's a couple of research trends going on. Different agencies are throwing out different numbers. Gartner estimated that at the moment 30% of the companies worldwide doing something in IT are kind of doing it on the cloud. Maybe not their whole deployments, but they're testing something on the cloud. And there's some kind of weird estimates that in 2 years' time, 75% of companies will be kind of using clouds for one thing or another. And when you're no longer working with hardware you control, when you're no longer working with any kind of infrastructure you control, the risk profile changes significantly. In my other life, about 15 years ago, I worked with companies that deployed stuff on immortal hardware that was never supposed to die. Everything was duplicated, triplicated. The storage cost more than everybody else in the company made in a year in salaries, and it was all brilliant. And then, when it fails, it's chaos. But now we're getting to the point where it's all commodity, it's all somewhere else's problem, and stuff fails all the time. And the whole kind of, every single architecture talk today at conferences is talking about Netflix, code monkeys, chaos gorillas, and things like that. Just, you were supposed to design software for being broken all the time. So I think that completely changes how we're doing testing, and a lot of the stuff we take for granted now, many things that we take as best practices for testing software today, really no longer apply in that environment. So kind of in terms of, Snow White and 777 as a story, I don't really have a story about that, but if we look at kind of any story, and if we look at really the purpose of testing today, I think testing is kind of an information act. It's about answering questions about what we want to do, and any story has questions it needs to answer. So I think if we're looking at this from a perspective of how testing is going to change, then there's some really, really important questions we need to start answering, like in any story. Who's done it? What have they done? Where is it? And things like that. So the first question is who, and I think that the question we need to talk about is who is using our products. That's changing significantly, and it's going to keep changing and changing and changing. One of the most exciting things for me personally that's happened last year is Amazon launching the API marketplace. The API marketplace is like an app store for APIs. The same stuff that Apple has done by creating an app store where anybody can kind of do an app, and then they're going to take care of billing, account management, distribution, and things like that. That's what Amazon is trying to do for APIs. Now, if you have a smart idea for an API that other people might want to use, they will pretty much handle the whole boring part of, the business side of things, not the business, the kind of operation side of things, where we can focus on building stuff that makes money. So kind of for a lot of things that I think is going to happen in the future with more cloud deployments and things like that, who is using our software is going to change. Because API consumers and everything is going kind of to third-party services, third-party APIs. A lot of us will be building APIs for other people to use. And one really, really interesting example of what happens when you change who is using your software comes from a book called The Making of Fly, The Genetics of Animal Design. Now, you're probably thinking that I'm crazy, and this is a book that was published in 1992. And that's really, really important for this story, because by the time this book became important for software testing, it was already out of print for about 10 years. Now, with modern services, kind of books never really go out of print. You can always add more, but books printed in 1992, you sell whatever you had to sell. there are no more new books in the market. Now, what Amazon also does is Amazon kind of doesn't just sell the stuff that they only have, because nobody has this book anymore. What they allow people to do is sell the stuff they have at home. Sell, if you have a copy of this book, you can sell it on Amazon. They'll take care of the billing. It's kind of similar to what they're trying to do with API marketplaces. And there was a guy called Professor Nath about 5 years ago who had a copy of this book and started selling it on Amazon. Nobody else had any copies of that book anywhere else. The other thing that kind of cloud opens up as a possibility, especially kind of marketplaces like this, is there are companies that are going to try to sell you every single thing that's sold on Amazon. They don't have it. And what they're betting on is that you will look for reputation. You're not going to buy from somebody who's never sold anything on Amazon before. You will look at somebody having 5 stars in reputation, and you will pay slightly more to buy from them. So what they do is they algorithmically look at everything that's being sold on Amazon, and they add their offer as well at about $5 more expensive. And their plan is if you do actually buy that from them, they'll go and buy this book from Professor Nath and get Professor Nath to send it to you. Free money. So kind of the irony of the whole thing is when Professor Nath put this book online, he was the only one who had a copy of this. This company called Book also said, well, we're going to sell this thing as well, $5 more than Professor Nath. Professor Nath, although, was not a complete idiot, and he knew that he doesn't know how to price this book. And he used a service that's an API on cloud that allows people not to waste money if somebody else to be the most competitive price in the market. So they're going to make the price the cheapest possible, but in order not to lose too much money, you can say, I want to be like $1 cheaper than everybody else. So here we have Book that says, I want to be $5 more expensive than the cheapest one because I need to buy and sell it at a profit. And we have Prof Nath using a service that says, I want to be $1 cheaper than the next offer. So he starts selling at 20, Book says 25. Prof Nath's algorithm says 24. Book says 29. He now says 28. These guys say 35. And this went on and on and on for a day or two, and they ended up kind of selling stuff for, competing at $1 million or something like that. After a couple of days, they got to the point where one of them is offering it at $23 million. Now, this makes this book officially the most expensive book in history. And the reason why we got to this point is that we have such good heuristics for trying to figure out what happens when humans are using our software. But when algorithms start using our software, the game changes completely. And 2 algorithms can get into a self-reinforcing loop really, really easily and do stupid stuff like this. Now, the big problem, as I said, is who's using our software is now changing. And many of the heuristics we have around how people use the software, how quickly they can use it and things like that, they will have to change as well. There was a famous case of a trading company on an exchange where somebody was using a click automation software to automate stuff on the screen, and the click automation software double-clicked too quickly. Because it double-clicked too quickly, the software thought that they tried to order something like 10,000 shares and then cancel everything, and the system went into a crazy loop. So when algorithms start using our software, the whole thing changes significantly. And now you can sit here and think about, we're not going to work with stupid professors and stupid book sales, and this really doesn't matter because, we're a big bank and banks don't have to deal with these things. And an example I'd like to use it to counter that is the example of Navinder Singh Sao, who used to live with his parents in Hammersmith in London. He used a Hotmail account to trade on the stock exchange, and he was reasonably good developing software, so he developed his own software for trading. And in 2010, his software sent 19,000 orders to the broker to buy and sell shares. What happened then was called by pretty much all the financial press in the world as the biggest stock exchange crash in history, because the New York Stock Exchange lost trillions of dollars in a couple of minutes, then it recovered, and then it lost it again. We're talking about 19,000 transactions. It's kind of nothing. His 19,000 transactions completely confused the trading algorithm used by big banks all over the world that started selling like crazy and thought something, serious is happening. And the US economy basically collapsed completely in 1 hour and then recovered magically. And it took them 5 years to figure out, that one guy living with his parents in Hammersmith caused the biggest kind of financial crash in history. Of course, they arrested him, and they threatened him with something like 320 years in prison. He has still not been sentenced. He's been in jail for about 2 years in the US. They've extradited him, and he's still not been sentenced, so who knows what's going to happen to him. But the really, really interesting thing is if one person living with his parents can crash the New York Stock Exchange, the whole profile of risk changed, people. It's something we need to be aware of. So and again, I think, having 19,000 transactions committed to the exchange quickly is really not a big problem. The problem is the algorithms are doing it now. So the risk profile changes. So the second thing that of course, if you look at him, they showed him in a hoodie because hackers are always in a hoodie. But he doesn't look like a kind of dangerous hacker at all. So the second thing that we really need to consider is the question of what are our products doing now. Now, there was a talk this afternoon where people said big data is always shown in blue, so I found a picture that's kind of blue and with a lens flash showing big data. And a lot of what our products are doing now changes because storage is so cheap. Because we can collect a ton of data, everybody's collecting a ton of data. And in 2015, Target, the US supermarket chain, were able to guess that a girl was pregnant a week before she understood she was pregnant and start selling her kind of baby supplies because they had this data. Now that story made news all over the world, and everybody that I know started talking about, we need big data. We need to do machine learning. Everybody's doing machine learning these days. And there's some incredible stories about what machines can do when they learn stuff. Also, image recognition has improved significantly. Now we are reading news about supermarkets getting your facial expression when you go in and figuring out what you want to buy. There was a news article 2 days ago how they've made a image recognition algorithm that can spot gay people with 90% accuracy. So all these things are incredible that are happening. But if you look at more serious stuff, everybody's talking about how algorithms are going to replace taxi drivers and things like that. Algorithms are, taxi drivers, nobody cares. Algorithms are going to replace doctors. Algorithms are going to replace people who study for 15 years and invest $500,000 into their education to be able to earn a high salary. There's a paper published by Google where their image recognition team used the data from the Radtown University, or that medical university. They have this database that's used to test radiologists, whether they can spot cancer on images. And the best human radiologists achieve the result of something like 73%. Google's algorithms spotted 89% accuracy cancer in images. IBM published research 2 years ago that together with some Japanese Japanese university, they were able to get Watson to recognize leukemia from medical data better than trained doctors. So those kind of professions are going to be replaced with image recognition algorithms very, very quickly because computers can recognize images much better. They can look at millions and millions of images quickly. They can compare images over time. The best trained radiologist ever can look at, I don't know how many thousands of pictures in his life. Where you can have Google's algorithm looking at millions and adding to that, and they're going to be better and better and better at this. And this is what we're going to get with cloud. First of all, there are already services for image recognition out there. There's Amazon Recognition and things that you can use for almost free now. Storage is cheap. Pretty much, something like that is going to be forced upon us by our companies very quickly. And then the question is, how do we test for things like that? How do you assess accuracy? And I love kind of telling people the story of Alicia and Allison Kennedy. Alicia and Allison Kennedy are two 16-year-old girls last year. They live in a place called Evans in Georgia in US. And 16-year-old kids in the US, the first thing they try to do is go and get a driver's license. So what they did is, after the 16th birthday, they went to kind of the local driving services office. They wanted to start getting on, the test path. And the first thing you need to do is you need to sign up for kind of taking the test and things like that. Both girls did the papers and submitted their photos. And the lady kind of processing that said, no, you need to take a photo again. And Alicia went and took a photo again, then they put her application, and then Allison had to go and take a photo. And then they did it a few times, and then they said, well, you need to kind of sign again, and you need to sign again, you need to sign again, you need to fill in the form again. And after about 2 hours of this, the computer basically just gave up and said, call headquarters. And the clerk called the headquarters and they said, no, you have kind of the anti-terrorist database has flashed like a fraud there. You need to stop doing whatever you're doing and we're going to send people to investigate. It's like, what's going on? And the trick is, Alicia and Allison are twins. And the computers couldn't tell them apart. They thought they were the same person. And they thought that the same person was trying to apply under two different names and kept refusing one of the applications. And then after 500 applications refused or whatever, it complained about anti-terrorist danger. They look very dangerous. And they had to shut the whole thing down. So this whole image recognition thing, yes, it's magical, but how do we test for something like that? And I think this whole idea of algorithms and machine learning and voice recognition, image recognition, and a ton of other things make it really, really difficult to assert correctness. Our testing practices over the last 15, 20 years have built around the fact that we know what the correct result is. We can assume what the correct result is. If you have a machine learning stuff and throwing results at you, how do you even know if that's correct or not correct? There's an interesting legislation going through the European Parliament now where they want people to get the right to an explanation. If a machine refuses your mortgage, or if a machine says your insurance premium for health is going up 10% this year, or your car insurance is increasing by 20%, you will need to get an explanation. There's no explanation. Machine said yes or machine said no. I think the whole thing we're doing now, there's a ton of these even open source machine learning toolkits, but how do we test for that? How do we assert correctness? And I think that's another thing that changes quite a lot. So the next question I think is really, really interesting to consider is where. In terms of where is the risk today in applications? And when we talk about where, of course, in computing, we can talk about, is it in the server, is it in the network, is it in the client, is it in the cloud? But the more interesting question of where is geography. And I put to you that the biggest risk is in a town called Potwin. Potwin is a town in Kansas, and it has about 430 people, which doesn't sound too dangerous. James and Theresa Arnold rented a farm in 2006 in Potwin because they wanted to move away from civilization and go somewhere where it's rural. They didn't want to be in a big city anymore. They rented a farm slightly outside Potwin, and the next day they got a phone call from somebody complaining that they can't send their email. Okay. Then 2 days later, the police came by looking for a stolen mobile phone. Then 2 days later, the anti-terrorist unit came by looking for some escaped terrorist. Then they started getting these really, really weird visits by the police looking for Bitcoin scams and things like that. And they didn't even have a computer on premise. That's really, really interesting. So I don't know how you can do Bitcoin scams without a computer. And this kept happening and happening so much that the local sheriff had to go and put up a sign in front of the farm saying that if any government agency wants to kind of harass these people, they have to go and talk to the sheriff first. And this kept happening over and over and over and over again. The sheriff got so pissed off. Every week he received requests to go there. And somebody even left a broken toilet in their kind of driveway as a revenge for I don't know what. And it was really kind of curious. Nobody knew why. It looks like the farm was cursed. And the whole thing unraveled when a guy called Anthony Pav complained about something very, very similar in Ashburn in Virginia. Anthony Pav came back one day to his house and saw the American SWAT, the Robocops breaking into his house. And said, don't break the door, I'll open it, that's fine, go and find whatever you want. And they were looking for a stolen government laptop. And, of course, they turned the whole thing upside down, they couldn't find anything, and they left. And he was curious why that happened, so he started researching that, got in touch with some journalists, and a journalist called Kashmir Hill from a magazine called Fusion finally figured out what's going on. What started happening last 10, 15 years with cloud, with online connectivity and everything is kind of these devices phone back home. You have Find My iPhone, you have kind of all these kind of protection things. If somebody steals a government laptop, the laptop is going to say, hey, I'm here. And the thing is, what also started happening is then it became important for marketing purpose and other things to figure out when somebody, talks to you from an IP address, where are those people? So we started getting services like MaxMind that give us a approximate geographic location for an IP. IP addresses were never ever designed to be in a single place geographically. But hey, now we have services for that. Then you have other services that translate geographic kind of coordinates to a physical address. And then governments start buying these things where, you mesh up a bunch of databases. You give people where to go for an IP address. So the stolen computer phone back home from Anthony Pav's house, and the police went there to break it down. Now, of course, it wasn't actually in his house, but Ashburn, Virginia is actually home to Google Cloud. And Google rents kind of spare capacity. Now all cloud providers rent spare capacity. People use VPNs. And if something stolen phones back home from a VPN, it looks like it's phoning back from Google Cloud. And with such a nice mashup of services, MaxMind actually doesn't know where all the IP addresses are in the world, of course, but they do an estimate. And if something is in Ashburn, but they don't know exactly where in Ashburn, they will put it smack in the middle of Ashburn geographically. And smack in the middle of Ashburn is Anthony Pav's house. So whenever anybody did any crime through the Google Cloud, his house would show up. Now, Kashmir Hill started kind of researching this, and he got in touch with the Arnolds to see if they had any problems. And they said, yeah, why are you asking about this? He said, well, if you look at this from a perspective of what these databases are doing, if MaxMind knew that the IP address was in the US, but not exactly where in the US, they would put it smack in the middle of the US, which unfortunately was Ashburn's farm. So there were 600 million IP addresses pointing at their house. Now, who is to blame here? The really interesting question is, first of all, MaxMind never offered the geographic address. They offered a latitude and longitude. Some other database kind of mashed this up. Is the other database to blame for kind of giving this wrong? Is MaxMind to blame for doing this? Is the government wrong for using a stupid system like this? And the big thing is, a lot of the cloud stuff we're doing today is just mashing up different services. How much do you actually trust the data you're using from a third-party service? How are you ensuring that, 99.9999999 times it's okay, but hey, it also has 600 million IP addresses pointing at a kind of house where nobody lives. Or, there's no computer there. So I think kind of what really is changing here is risk is shifting from units to integration tests. And to kind of third-party systems. And the practices we were using for the last 20 years are all talking about how, you do most of your testing with your code units. But if your code unit is adding up 3 different services together, there's not a lot to test there. And the risk is no longer there. The risk is somebody kind of giving you bad data. So the next question I think we need to consider is when. This is when do risky things actually happen? For example, 2 years ago, I was flying through Paris, and one of my favorite restaurants in the world is in Paris. Of course, they have good food there. And I had about 4 hours overlay, so that's just enough to, when I arrived there, go to the city, grab a nice meal, go back, done, victory. And as I landed in Paris, I connected my phone and I got something like 500 emails from a monitoring service that shit's broken. Which meant that, I couldn't go and have a nice meal. I had to go open up my laptop on a stupid Wi-Fi in kind of the Paris Charles de Gaulle airport that just doesn't work and disconnects all the time, and try to troubleshoot this and figure out what's going on. And the product that I'm kind of working on at the moment is a mind mapping tool that allows people to store stuff, among other things, to Google Drive. At some point during my flight, Google had a new release of their kind of Drive software that changed the order of events, completely broke everything we're doing. People couldn't log in anymore. And kind of the whole thing was a mess. So rather than having a nice steak in Paris, I had to kind of troubleshoot stupid Google software that, I wasn't guilty that that changed. It's somebody else's fault. But then again, Google doesn't care about me. So whose problem is it? It's my problem, of course. So I think a lot of what we've done in the last 15, 20 years is test things to be bulletproof before releasing, where a significant amount of risk, as kind of it's on the cloud and it's using third-party services, it's communicating with everybody else, happens after we release. Your code will not need to change for problems to arise. And that comes, now starts having a completely interesting risk profile. So kind of in terms of putting stuff into the cloud, to really get the benefits out of that, yes, we can ignore all those third-party services, but this doesn't make any sense. Because cloud is no longer kind of virtual machines. Cloud is now the whole ecosystem. Amazon released Cognito about a year ago that does fully managed user accounts, two-factor authentication, federated logins. It's basically your first 3 months of developing a new application offered to you as a service for almost free. It costs $5 per million users. It's ridiculous. So there's kind of pointless to develop your own user database, especially if you are already deployed on Amazon or already deployed somewhere like that. It's just perfectly logical to use a service like this. Why would you develop your own image recognition when you can just buy it from Amazon? Why would you develop your own monitoring stuff that you can just get for free from Amazon? And things like so. Cloud 10 years ago was give me a virtual machine. Cloud today is a whole ecosystem for running the applications. Simon Wardley, who is kind of a researcher in the UK and writes a lot about cloud and things like that, talked about how kind of serverless, whatever the buzzword is the first first really good implementation of platform as a service. It's going to be using the platform for authentication, for logging, for monitoring, for everything apart from 20 lines of business code. And there kind of the risk changes completely. These things happen, changes to those software happen after you go live. So kind of the major risks, I think, are no longer going to happen before we deploy. The major risks are going to start happening after we deploy. And the whole purpose of testing and getting information out will need to change. So kind of the next question that I think we really need to consider is how do our users interact with us? And I think given the kind of all these services that are emerging and how we're getting the different devices and things like that, that's completely going to change. And how we test our software is completely going to change. Now I'm going to need your help with the pronunciation. There's a kind of, is it Nanyang Technical University, or how is it called, the thing that's a couple of kilometers from here? Nanyang, yeah, okay. So in Nanyang Technical University a year ago, kind of this photo was taken. I don't know if you guys in Singapore know kind of these two ladies. This is Professor Nadia and Nadine. Nadine is actually a robot. Nadine is a robot receptionist they've put in the Nanyang Technical University to welcome people, and she can move, she can bring coffee, she can talk. And kind of this is kind of the two of them. You can see that Nadine is a bit bored, but I guess that's what Douglas Adams predicted with, android paranoid robot Marvin, who's always bored because he has kind of better computing capacity than everybody around him. So, there's the professor and her robot that can calculate the universe. And
hello, nice to see you. What is your job?
I am a social companion. I can speak of emotions and I can recognize people. I recognize you, Nadia. Nice to meet you again today.
So, we have robots now welcoming people to universities. By the way, in the Science University now, until kind of the 15th of October, if you go, you will see her. She's on exhibit. So we have robots now interacting with us. All the heuristics we had around, you put an umlaut and a null and things like that on the keyboard. Where's the keyboard here? How do we test this? And we can talk about how you might not kind of want to need that and this is never coming and things like that, but things like this are going to force people to start considering different interfaces. Who has an Echo at home? Does anybody have an Echo at home? Okay, we have a couple of people here. So this is absolutely amazing. Amazon Echo is kind of a voice box that talks to the cloud. My children use it all the time. Kind of they argue with it, they shout at it, this thing reads them stories, it kind of plays music and things like that. And when it came out, people were overly obsessed about, this doing news and things, but I think for most people, actually kids are playing with this now. And this is a fantastic way to, keep your kids quiet for a long time. And kind of the interfaces around this are really, really interesting. Because now we have a voice interface. How do we test for this? How do we, what are the heuristics? And there was really, really interesting research published a few days ago where there was there's a university in the US where they've tried to trick this and Google Home and Siri and a bunch of other kind of voice interfaces with sounds that humans cannot hear. They were kind of doing subsonic sounds, then, were able to purchase things through Amazon, were able to kind of shut down people's homes. These things are connected to locks, they're connected to lights and things like that, and stuff that you and I cannot hear at all, they were doing remotely to, lock your home. How do we test for that? And kind of, I told you my kids are playing with this all the time, and my daughter is, picking this up and shouting at it when it doesn't understand it and things like that. And they're actually amazing. I'm amazed that, you can make something like this understand my broken English with a Russian spy accent, my son's English that's a lot better, my daughter's English, they grew up in the UK, so they speak English properly. But kind of, there's a girl called Brooke Netzel that's 7 years old. And Brooke, like my children, started really, talking to Alexa as if it was a live person, playing with her. And, so, okay, casually, Brooke, was playing with Alexa and said, oh, Alexa, what I'd really like is a dollhouse and some cookies. And, Alexa delivered. So next morning, she got a big, big, big dollhouse worth about $170. And a massive, massive box of cookies. So, now, the story would be funny enough if it ended here, but because this happened and then the mother complained to Amazon and things like that, it got into the news. And in a San Diego TV station, kind of 9 p.m., everybody's busy watching news, a journalist said, and, there was this girl in Dallas that said, oh, Alexa, I'd really like a dollhouse and some cookies. Thousands of Alexas all over the US started ordering dollhouses and cookies because they heard the news. Now, this is kind of course, completely insane. Nobody predicted that, but that's the whole point. Voice interfaces are completely changing how we test software. And you can now sit here and say, well, it doesn't matter because we're a bank and, we're never going to start looking at this. But I think there's a lot more to this. I think we are fundamentally changing how we interact with computing. Look, if you look at keyboards, keyboards are a historical curiosity that's existed last 150 years. That's because, it was difficult to read when doctors write whatever they need to write, so they invented typing machines, we got keyboards, but that's a historical curiosity. For thousands of years, we've communicated using pictures, using voice, using touch. And, computers were not good enough to recognize that. 10 years ago, we got an iPhone because it was good enough to recognize touch. Now we're getting voice. With image recognition, with things like that, we are getting different interfaces. And maybe it's not going to be voice for you. Maybe it will be something else. But the big question is, how do we don't have any testing heuristics for this. As a testing community, we know that's not evolved at all. So we have again, you can sit here and say, well, as a bank, we're never going to have a problem with this. But as a counter argument, I give you HSBC in the UK. HSBC launched Voice ID last year. Whenever I log on to HSBC, especially if I do phone banking, there's kind of this thing, would you like to activate Voice ID? And I have always done that. No. And they're really confusing. Can just...
Voice ID is a new way to bank over the phone without having to enter your account details or answer any account verification questions. Your voice is unique. Our software can analyze over 100 unique features, from your pronunciation to the tone and pattern of your voice. It can recognize you even if you have a cold or sore throat.
This sounds absolutely amazing. It can recognize you if you have a cold or a sore. I can't recognize myself when I have a cold. And it can recognize me. Machines are so good with this. I'm scared shitless when I hear something like this protecting my bank account. Because I'm a software developer. I can think of 5 million ways of this going wrong. And of course, people said, oh, there's 5 million ways this can go wrong. And HSBC said, no, we tested this. It's 100 different patterns in the voice. Nobody's going to be able to break this. 5 days later, Joe and Dan Simmons is a journalist from BBC Click, were able to trick HSBC Voice ID. Can anybody guess why? Nope. They're twins, of course. So now we have twins emerging as a universal edge case in cloud software today. So they're twins. And nobody tested against twins. So now this becomes really, I think, this whole thing is going to start changing how we look at software. So the first thing that I think is really interesting is testing pyramid. That we've seen 5 testing pyramids at this conference. Everybody's talking about the testing pyramid. The testing pyramid is no longer relevant at all. The risk is not in the units anymore. The risk is in the integration. The whole test your code, don't test the top layer. Well, if your top layer is voice, your code is irrelevant. It's the testing pyramid is I don't know what now, really, because it's completely changed. The other thing that we need to start considering is how much does it cost to run integration tests? If we do want to run all these tests end to end, historically it was stupidly expensive to do that, but now compute is almost ridiculously cheap. We can run stuff on Amazon. I can run 20,000 machines to give me my UI testing in about 3 seconds. Is it still expensive? Is it still slow? The whole purpose of the testing pyramid was there because UI testing was slow and expensive. Now when UI testing is cheap and fast, do we really need the testing pyramid anymore? The second thing that's really interesting is with risk moving from before deployment to after deployment, I think a lot of what we need to do in testing is move away from predictive stuff like, assert, we're done, to active monitoring in production. If we're trying to defend against third parties giving us bad data, if we're trying to defend against somebody going into a cycle with our algorithm and getting the price on Amazon to 23 million, we need to monitor for stuff like that in production. We can't predict it. All these things are not depending on us. They depend on other people. So, 5 years ago when people were talking about, we test our software in production, everybody thought, well, you're an idiot. That's horrible. But if 90% of your risk is in production, well, that's why you need to test your software. Now, the really interesting part of this, again, is with services like Lambda, with, everybody there's lots of talks about Lambda here. Having another copy of your production is ridiculously cheap. So why not do that? Let's test in real life. So one really interesting thing to consider about this comes from a game called No Man's Sky. This is No Man's Sky. If you play video games, This is one of the most exciting things that happened, and then kind of somehow it died out. No Man's Sky is a generative universe exploration game. They created about 18 quintillion worlds to play in the game. I have a BSc in maths, I don't know how much a quintillion is, sorry. But 18 quintillion is a lot. And each of these worlds is supposed to be playable for months and months and months. You're supposed to be able to drive your rocket and explore it and things like that. Now, what they've done is, to make it interesting, they've taken some designs of animals and things like that, and then they've applied mutation to it. Like, get, an armadillo, get it to stand up, paint it red, make it more interesting. How do you even test whether that makes sense? How do you test all these 18 quintillion worlds where each of these takes months and months to fly through? So what they've done is they've built probes, very much like NASA explores space. And these probes randomly jump around this universe, they fly around, and they take videos of what's going on. And they have about 30 monitors in the developer's room, and they show those videos all the time. And then when people say, oh, this is weird, it doesn't make sense, we have a lion with chicken legs, stop. Then you kind of figure out why. You look at, improving the algorithm, and you run it again. And I think because we cannot predict what's correct, what's incorrect with machine learning, we cannot predict a lot of other stuff, a lot of what we do will have to start moving more to kind of approvals rather than verification. It's going to be difficult to say this is the expected result. It's going to be much, much easier to say, well, this looks okay, I approve it, I don't approve it. And again, I think this is where a lot of kind of what's happening in the cloud, making compute cheaper, is going to make it really, really interesting. For example, this kind of mind mapping tool I'm working on at the moment, we've started adopting this approach quite a lot, where when things move around, previously what we had to do is sit down and do a lot of maths to figure out whether the coordinates are correct, what's the expected result. This was slowing us down quite significantly. Maintaining our tests was hurting a lot, and we started moving a lot more to kind of visual approval tests. This is kind of a tool I'm actually building at the moment, and it's good enough for us. It's not yet good enough for everybody else, but we're in the process of kind of releasing it. And this thing is going to go and kind of take lots of screenshots, cut them up, and compare images with expected results. And if anything moves, it's going to show you, like, this was your expected, this is the actual, this is the diff. Is this what you wanted to do with this code change? Is this okay? Is this not okay? And then if it looks okay, you can approve it. And that becomes the next baseline. Now, stuff like this is technically not new. Tools like this existed, 20 years ago. They were too expensive. And your brain, like, my brain was fighting me 6 months ago, is probably telling you now this is going to be stupidly slow and expensive to run. But I can run this on 10,000 machines in Amazon in parallel. And it doesn't cost anything. So, is it still too expensive and too long to run? And if we can do stuff like this, do we still need all these, tiny coordinate mathematical tests that are messing things up? So this thing is on GitHub at the moment. I'm kind of open sourcing the stuff we've built. And in about 10 days, I think it will be ready for people to start using. But I think we're going to see more and more of these tools emerging now, because compute cost has changed, the risk profile has changed. One other thing that's changed the last couple of years is machine learning. Yes, it's a problem, but it can also be applied to help us with the code. MIT did this thing where they've applied machine learning to figure out, can they teach a machine what is a bug on the source code? And they ran this thing on GitHub repositories, on issues, and they let the machines learn what bugs are and how to fix bugs. And they've built this kind of code helper that goes through your GitHub repo and submits pull requests saying, oh, I fixed the bug. Based on, I don't know, kind of, the right to explain is not done yet in Europe, so who knows? But I find this really, really interesting, and kind of this is still research, but I think kind of, okay, maybe we're not going to get machines fixing bugs, but we can apply machine learning if we're talking about the search space being too complicated. Like, ton of stuff unpredictable, lots of code, lots of services. If we are going to go for approval testing, we need to know where to focus. Otherwise, it's too expensive and too long. What if machines could actually guide exploratory testing? And I hope we're going to start getting algorithms like this emerging that it's going to look at your bug database and it's going to say, well, you know, statistically, whenever I see something like this, there's a bug on the screen. I don't know what the bug is, but maybe go and explore that screen now, rather than wasting time on everything. And I think that's going to be quite powerful. So in conclusion, I think kind of cloud is you know, poses a massive, massive challenge for what we're going to do with risk profiles, what we're going to do with testing, where to look for stuff. But it also opens some serious opportunities around inverting our testing pyramids, making things that were stupidly expensive before ridiculously cheap now. And I hope we're going to see a whole emergence of different testing practices. So thank you very much. This is kind of all I had for you. I hope I've challenged your thinking at least a bit. And I think I ran out of time, so I'll take questions outside. I'll let the next speaker take over. Thank you.